In this clip, we're not only getting the gateway ID, we're also going to create segments for the floors and ceilings. Now when it comes to the gateways, we can't just use the same logic as with the corridors. There we used intersect to see if we find the opposite side of the corridor. But the gateways have open entrances, so there's a space where the intersect can't find anything, even if it's in fact a gateway. The solution is either the floor or the ceiling. I'm going to use the floor and connect it to a fuse node. Again, so that primitives that are beside one another share the same edge points. This will take up quite some space, so create a subnetwork. Here we'll mark segments in the floors and the ceiling. But to do that, I have to connect the corridors as second input and of course also the ceiling. It goes into the third input. Then jump inside and let's start to cut this floor into pieces. First we create a wrangle, and this one will find all the floor segments that are touching the corridors. As the name implies, this wrangle needs the corridors as a reference, so they go into the second input. This one will use once again point clouds, so you should know by now how we start. We need a point array, the point cloud handle, a position vector, and integer variables for the found points. Make sure that this one is a primitive wrangle and then get the points of the current primitive. It's quite important that the int variable check is initialized before we continue. Then we go into the loop, get the position of one of the floor points, and start the point cloud to find the points on the corridors. We don't have to look very far, and I give a high number for the possible points just because I don't want to limit the result. I put the number of the cloud in the variable found, and I add that number onto the variable check. Just for a better image for what is happening right now, when I create a null and put it between the second input and the wrangle, I can show you the corridor geometry as a template. We basically let each floor primitive count the points of corridor points that are close to it. Now the pieces that are interesting to us at this point are the ones that have the most connecting points, or at least 2 of them. If the floor primitive has at least 2 points connecting with 2 corridor points, this primitive gets a new attribute called stay. The value for that primitive is 1. At the same time, we're going to set the attribute structure to corridor, since we know at this point this is part of a corridor. And again, we can now close the point cloud. Now we can single out all the floor parts that are near the corridor. Just take a blast node and select all the primitives that have the attribute stay equals 1. That also gives us all the floor parts that are not connected with the corridor. Just copy the blast node and reverse it. As I said before, when you name your nodes beginning with a capital Out, these nodes will be at the top of the list, and it can be any node. Now later on we will need these floor parts, but minus the last primitive. So let's create a new wrangle that will delete that last one. That means I can name this node out floor outer corridor -1. This will be a quick and easy one. I need a point array and an int variable that holds the amount of neighbors. The points come from the current primitive, which go right into the loop where I get the neighbor count of each point. Whenever that count is equals 2, that primitive has to be at the end of the corridor, which means I can simply remove that primitive. By having the outer corridors minus the last piece, it's very easy to separate the last floor primitives. I still need the middle corridor and the gateway floors by themselves, and I can find them with one more wrangle. After the wrangle, I want to be able to select the complete middle floor, the middle floor -1, and the gateways. As I said, I need the floor outer corridor -1 as reference, and then jump into the editor. Again, it will be a point cloud operation. And somehow I have to react to 2 different amounts that the point cloud returns. I grab the points of the primitive and again go into the loop. When I'm inside of the loop, I get the position information of that point and open the point cloud for the second input. Since the points once again overlap, I only need to look for a very small distance, and I'm only looking for one point. If the function PCNumFound returns that it found that one point, I add 1 to the integer found variable. Now, after the loop, I'm going to set the attribute stay according to the value that was saved in found. If that value is bigger or equals 1, the stay attribute is also set to 1. If found is bigger or equals 2, the same goes for the attribute stay. And for good measures, close the point cloud after you don't need it anymore. And we got an error because I didn't use two different found variables. I solved the issue with two different states on the attribute stay, but only with one int variable for found. Now it should work. I should be able to get the 3 different sets of floor pieces. So create a blast node and delete everything that does not stay bigger or equals 1. That is the first set. Now copy the blast node, and if we change this to stay is equals 1, we can see the 2 primitives on each end where that's the case. So if we change the second blast node to bigger or equals 2, we should get the middle corridor pieces -1. That's the second set. The third set that we need are the gateway floor pieces. Those are all the pieces where stay is equals 0. We will need those different pieces later when we design the floors in the corridors. So again, it's very helpful to name these nodes beginning with a capital Out. Now the only combination of pieces we might use later on would be the complete floor. We need to merge the 2 nodes that hold the outer pieces and the middle pieces. So go to one of those blast nodes, connect it to the merge, and then wire up the second one. And with that we have all the segmentations we might need. But what's with the ceilings? Until now we only work with the floor. The good thing though is that this complete network just works no matter if we feed in the floor or the ceiling. So create a box for these nodes, call it segmenting the floor, copy the box, and now we can reuse the complete box and simply wire in the ceilings instead of the floor. Disconnect the floor fuse node. This null now brings in the corridor for both network boxes. And then we can grab the ceilings from the third incoming input and give them a fuse node on its own. A quick check if we indeed have the ceilings right now, but that seems to be correct. So wire in the fuse node into the first wrangle node. And all of our segmentations should work the same. Each operation from start to finish is related to the distance of the incoming primitives to the segments that we want to separate. Again, don't forget to keep your project organized. Whenever you copy a bunch of nodes, you should always remember to rename them to what they really do. Now this subnetwork created quite a bunch of outgoing nodes. When doing a project on your own, you'll find yourself visiting these networks quite often for refining and tuning the process. That might become a problem if that subnetwork is incorporated into the process. If you remember, I still need the floor of the gateways to somehow get a gateway ID. That means whenever I come back into this network and leave it without setting the visibility flag on the floor gateway, I might break my project by accident. A simple way to prevent that is to create an output node right after the last node of your network. This way, when you jump out of this network, you always see the gateway floors, even if you have the visibility flag on any other node of the network. So let's continue to the next clip where we use that floor.